Unit 3 is on solving systems with linear combinations. Linear combinations means you're going to take your system and you are going to combine the two equations into one equation you can solve. So basically you turn this into a giant addition problem. You need to make sure that your x's and your y's are lined up, and they are, x and x, y and y, and constant and constant. You're going to turn this into a giant addition problem, and you're going to add down by combining like terms. So 2x minus 2x, that cancels out and because you get 0x. Y minus 7y is going to give you negative 6y. Keep the equal sign in the same place and don't forget you're adding down. So 5 plus 13 gives you 18. Notice how this cancels out. Another name for this method is elimination. When you combine your equations, a variable should be eliminated. In this case, the x was eliminated, leaving us with just a y and a very simple equation to solve. We divide both sides by negative 6. Negative 6 over negative 6 is 1, so you get 1y equals 18 divided by 6 is 3. The 6 is negative, so I get negative 3 for y. Now, remember I'm solving a system, so I should have a coordinate for my answer, an x and a y. I have the y, but I still need to figure out what the x is. So you go and pick one of your equations that you started with. Pick whichever one's looks the easiest. Like, I'm going to pick the first equation because everything is positive. Sometimes I make mistakes with negative numbers, so let's make it easy on myself and pick the one that has positive numbers. So I'm going to take 2x plus y equals 5. I know that y equals negative 3, so I can plug in a negative 3 where the y goes. And then I solve for x. So I add 3 to both sides, and I get 2x equals 8. Divide by 2, and I'm left with x equals 4. And that gives me my coordinate. 4 comma negative 3 is the solution to this equation. Here's the second example for 8.03. If you start out the same way I showed you before, you're going to turn this into a giant addition problem. When you add down, you get 5x plus 4y equals 47. Notice how there wasn't a variable that was eliminated. The equation that you get when you combine them is not simple like the one we had before. When that happens, this does not help you at all. So what you need to try to do is look at each equation and figure out how are you going to make it so that a variable gets eliminated. For example, if I could change this number right here, if that number could be a positive 6 instead of a negative 6, there you go, so you can see a positive 6 instead of a negative 6, those would cancel out with each other. How can I turn that into a 6 in a way that's legal? I can't erase the 2 and write a 6 there, but I can multiply the top equation by 3. And as long as I multiply everything in the equation by 3, equality will still be maintained. So I'm going to do 3 times 2 to get 6x, 3 times 2 to get 6y, keep the equal sign there, and then 44 times 3. 44 times 3 is 132. And I keep my second equation exactly the same as it was. So 3x minus 6y equals 3. Now when I combine them into a giant addition problem, I get 9x. The 6y minus 6y cancels, and then I get equals 135. So notice how a variable cancels out. That's what I want. That's my goal. If nothing cancels when you combine the equations together, multiply one of the equations by a number in order to get them to cancel. Like here I had 6 and -6, so they canceled. Over here I'm going to divide by 9. 135 divided by 9 equals 15. So x equals 15. Remember, I'm solving for a coordinate, so 15 is the x, but I need to know what's the y coordinate. So go back to your original problem, okay? And you either pick the top equation or the bottom equation, and you pick whichever one looks the easiest. I'm going to pick the top equation because they're all positive. Even though 44 is kind of a big number, I'm still going to pick the top equation. So I would copy over the top equation, which is 2x plus 2y equals 44. And I'm going to put in the 15 for the x. And then I'm going to solve for y. So 2 times 15 is 30, and I have 30 plus 2y equals 44. I subtract 30 from both sides of the equation, so it cancels on the left, and on the right-hand side, I have 44 minus 30, which gives me 14. Copy down the 2y. Last, divide by 2, and I get y equals 7. So my answer to the solution is going to be 15, 7. Okay, and to end 8.3. 8.3 is your mid-unit test. So when you go to take the quiz, you are going to have questions from Lesson 1, Lesson 2, and Lesson 3. So here's some brief reminders to help you on that mid-unit test. When you have a system, systems can have one solution, infinite solutions, or no solutions. When is a system going to have one solution? Well, if you're looking at the graph, it's when the lines intersect. And when you solve a system algebraically, it's when you get an answer x, y. If they have infinite solutions, that means you have coincident lines. It means that when you graph both of the equations on a graph, they end up being the exact same line, one right on top of each other. This happens when you're solving algebraically when the variables disappear and you're left with a true statement. Example, if you're solving a system, suddenly x disappears and y's disappeared, and you get 9 equals 9, that's a true statement. It means that there's infinite solutions. Likewise, no solutions. On a graph, what that looks like is parallel lines that never cross. When you're solving a system, if you're solving the system and the variables disappear and you get an untrue statement, that means an untrue statement like 3 equals 10, that's not true. 3 doesn't equal 10. When that happens when you're solving a system, you end up with no solutions. Okay, so those are your options. You can have one solution when you solve a system, infinite solutions, or no solutions.